So today there is a concert, jam after the midrasha at 5:30. There will be some wine and maybe beer. It's 6. Probably it's 6. Okay, so today I'm talking about the topic of today's lecture is about lattices in amenable group. So the מקליט? lattices in amenable group. That's the title of today. So I'm following if you want literature, I'm following the paper by Badel, Kapras, me, and Shachar Moses. And there is a lot of information here that I will not do in the course. I will focus on one issue. So that's the topic for today. That's the title of the paper. That's the title of the paper. You can find it on archive. And I'm focusing on basically on one question. The theorem of Mostov about lattices in solvable Lie groups. So why the screen doesn't show? Why something? Because Gil turned off the camera. Okay, so
Hi.
So maybe there is a speaker there that doesn't work. אולי כדאי להדליק את הספיקר שם, because I heard it from the computer. Or I can turn the volume. So, okay, let's just start. Mostov. Mostov has a paper, or maybe two papers about lattices in solvable Lie groups, papers in the annals. Also, he developed a theory of that, and one of the main results is the following. So let G be compactly generated, maybe some connected, which is almost the same thing. But I want to emphasize this property, compactly generated Lie group. So, by the way, here's an exercise for you. Well, let me say the theorem then. A compactly generated Lie group, let H G be a closed subgroup. Then the following are equivalent if you want. The following are equivalent. H is called compact. And H is called finite. So, Gil, can you read this? Itamar, can you read? Is it big enough?
Yeah, sorry, I was muted. I can read it. I can read it, yes.
Can read? But I see maybe this should be big. So these are so basically it says that the lattice in a solvable group is always co-compact And also it says that a co-compact subgroup in a solvable group is always cofinite. We know that this property, co-compactness, does not imply cofiniteness. In general,
solvable.
Compactly generated solvable, that's the main thing.
So compactly generated just means with the quotient with the connected
Let me just come to that. So just a remark to have in mind. I said it last time, but most of both theorem and both sides are non-trivial. Raghunathan simplified it proof by a lot, but still in Raghunathan's proof, both sides are not completely trivial. One side is easier today with the notion of amenability. So a remark, whenever if G is amenable, any co-compact. So some people don't like the co here, so maybe we call it uniform. So any uniform subgroup basically meaning that G mod H is compact is cofinite. And again, cofinite means that G mod H is finite G invariant measure, and that's immediately follow from amenability. This space is compact, so it admits a probability G invariant probability measure. It's one of the equivalent notions of amenability. Solvable groups are amenable, so that side follow from amenability, and it's will not do more than that. But if you want, you can read the proof that for Raghunathan it's better than. You can also it's also a good idea to look at Moscow paper. See the lemmas, it's useful. But okay, you can learn from the arguments. But this side basically follow from amenability. About tal question. So here is an exercise for you. General, a connected Lie group is compactly generated. In fact, more than that, a connected locally compact group is compactly generated. Trying to see how difficult is this one. It's certainly not very difficult if you use the structured theorem of locally compact groups. But just directly.
Have a proof of the first statement, which doesn't prove the second statement.
Yes. Okay. Yeah. No, connected, sure. Yeah, I mean, that's trivial. Yeah. Yeah, that's trivial. Okay, so, and basically, a Lie group is compactly generated if and only if the discrete group G modulo G naught is what usually people denote the identity connected components in a group, which is also a group, it's a normal sample, it's finitely generated.
Do you know, Gina, why is it switched? It's just disconnected.
For a lead group, it's discrete because yes, I mean by the definition of lead group, define lead group. Yeah. In general, Gmod is not totally disconnected. For lead group, the connected component of identity is also volatile. A lead group by definition is a manifold. So okay, so let's prove most of theorem. So I want to give an even. So Raghunathan once told me that his proof is much better, much simpler than most of proof. And actually, Borel told him that after he read Raghunathan proof, he understood the theorem. But you can even simplify Raghunathan. And before that, let me give a definition. After most of, or after Malchev, it's after most of, definition. A locally compact group. As property M. If co-finite implies co-compact. Locally compact group G. If if any uniform subgroup A in G is co-finite. And the G mod H admits the G. And M is after most of, and basically the theorem that we want to discuss is that connected or more generally compactly generated lead groups are a property, solvable lead group, with property S. And last time I told you the following theorem, which in the case of lead group was proved by Malchev. Malchev developed the theory of lattices in nilpotent lead groups. So we did a lot of this beautiful, elementary but beautiful theory, which demonstrates all the nice thing about lattices, including reductivity, rigidity, and so on. By the way, there is also some still a very famous open problem about lattices in important group, about quasi-isometric rigidity of such. If you want, I can discuss it. It's not something that I recommend you to work on before you finish your this.
Something I have a question. Again, this is one, the fact that solvable groups have property M, this is just amenability.
No, amenability implies the converse of. Yeah, you're right. So I thought I with any co-finite. Thank you. Subgroup. Co-finite or subgroup. Yeah, thank you. Amenability implies what was written before, which was converse of both. And we want to show that the co-finite implies both. Every lattice. And the theorem that we showed last time, which was very elementary, nilpotent groups. And what?
I mean, but like, doesn't that, like, basically in theory doesn't that prove that theorem comes proof? No.
No. Important. Now I want to prove for solvable.
But I mean, the G mod, like bracket GG is the positive, and the step going up we proved last time.
No, it's not. I mean, okay. The moral of today's lecture is that solvable groups are much harder than important. So I will prove. Okay. You will see. I mean, basically the question that I want to discuss is the following: are solvable through something groups admit do solvable group admits property. And you will see that it's much harder. And we have to understand that solvable is actually not enough. And even metabelian is not. You know, metabelian is solvable step 2. So the group which is homotype with abelian, not necessarily a property. But the important group is easier. And by the way, yeah. So that's what we did last time. And now, before discussing this in more generality, I would like to give a proof of most of theorem that connected or completely related solvable Lie group with property M. Before that, let me give you some exercise. So, exercise. And I would like to see a nice solution to this exercise. Because somehow I know how to solve it, but I'm not satisfied with my solution. It's a bit, seems to be a bit too complex. Basically, so the question is if Z or Zn, if Zn is the lattice in G, then it's co-compact. You can also discuss here we discuss a subgroup of a given group. You can also discuss, and people do, envelopes of groups. So groups that contain a given group as lattices or cofinite subgroups. And basically I want to show that whenever you have an envelope for Zn, then Zn is a uniform subgroup. So let me write it. So let G be locally compact group containing Zn as the lattice, then Zn is uniform. And basically start with Z. First do it for Z. I mean, that will be easier. But then Zn, somehow I'm not very happy with the way I see it. So I would like to see a straightforward proof.
I'm almost sure Uli and Dorman have a few.
You think? I don't know. I discussed this with Uli when we wrote that paper, and okay, I still don't have a proof that I'm satisfied. So maybe Roman and Uri studied envelopes of groups. Maybe they have.
The proof doesn't go through saying what G must be. Like it's G is
Sorry?
not highly restricted in this case.
Sorry?
But you know a lot of things about G, right? If you assume it has a lattice which is more from the way.
Yeah, even if you assume, okay, let me give you, you may assume, I'll be happy also if you assume locally compact, let's say even solvable, even, okay, that's somehow, let's call this number 3. And then let's containing okay. Let's do it. Okay. Even assume. Okay. First, let G be solvable, and if you want to assume even legal group containing Z and a lattice, then it is composed. Then it is uniform.
You want us to do it without most of theorem.
Yeah, without most of theorem.
That's the point. Okay.
Straightforward proof. So that would be, if you want 1, 2 will be a more general version of it. So let H be a compact. Okay, this would be 3. So let G be locally compact. Group containing H, which is and as a lattice, as a cofinite subgroup. Let me write as cofinite subgroup. Then H is uniform. And 3 will be the same, same as 2. Same for H compactly generated abelian. So I know 3 is the strongest statement. I know that it is true, but I don't have a nice proof of it. But the difficulty is already here. So if you find this, I know to do this reduction quite easily. So I don't have a nice proof. It depends what you call nice, but I don't have a very nice proof for 1. Once you have 1, to reduce 2 and 3 is yeah, more crazy. Also, 1 should be very elementary, but I don't. I'll be happy to say a proof. But let's assume that, because I'm going to use this as a data to prove most of somehow. If you want, you can argue that I push the difficulty into that statement, but it's not quite true, because even the proof that I know is not very hard. It's like half page. So it's much easier than the proofs in the literature of most of theorem.
I think in 3H is also a lattice, right?
Cofinite. So 3 is like 2, but instead of assuming that it's
No, but
Zn.
it's also a lattice. Yeah. I mean, it's necessarily a lattice. It's nothing to the end.
Yeah, cofinite subgroup is a lattice. Cofinite discrete. Lattice is a cofinite discrete. So I wrote cofinite.
If it's abstract, it's not to the end, it must be this.
Okay.
The reason that I wrote cofinite is because for 3.
Okay.
In 3, I noticed it's discrete. Because it's slightly more general. I don't even know why I insist on that generality, because most interested are the discrete cases. Lattices, not closed. Okay, that's one exercise. Another exercise which is good to know, is the following. So definition. So I don't know if I should use this term, and I would like to say that a group is Noetherian if every, let's say a discrete group is, you can say is Noetherian if every subgroup of it is finitely generated. Like the free group is not like that, but the end is. I would terms what? You know, like in commutative algebra, a ring is Noetherian if every ideal is finitely generated. So here I would like to generalize this notion, but it's not good to call it Noetherian. So let's say.
What kind of subgroup? You just said subgroup.
Let me just say a definition. So, but I need a name. So
Hereditary just
hereditary just hereditary group G as property actually completely generally HCG if every closed subgroup is completely general. So let's say that a discrete group, for discrete group, compactly generated is like finitely generated. So a discrete group, I would say HFG. And again, all these properties that I'm discussing are more interesting for discrete groups. So in a sense, I just told you, but I don't know why I insist on this generality. It's slightly more general, and it's not difficult to go from the discrete to the general case. But let's continue like that. And for instance, you can show that a abelian group, completely generated abelian group are always like that. But what is interesting is the following lemma or exercise. Connected solvable group or compactly generated solvable Lee group have this property H, C, G. If you have a solvable Lie group, if you have connected solvable Lie group, for Lie group, as I said before, to be compactly generated, it almost is to be connected. Just say that modulo the connecting component you find. So you can assume. So in other words, you can say, let me just write the corollary. The corollary is more famous than the exercise, but the proof is the same. If G is connected solvable Lie group and gamma in G is discrete, then gamma, of course, it's solvable, but it's also HCG or HFG. But for solvable discrete group, this has a name, it's called polycyclic. And gamma is what's the word? I, Y.
Y.
Poly, and now I.
Y.
It's like cycling.
This. What is a polycyclic group? So if you remember, a solvable group is a group such as there's a normal subgroup which the quotient is abelian, and this normal subgroup is solvable of smaller ones. So here it has a sequence. So I recall you that the group G, you have G, inside you have G prime, inside you have G double prime, so on, until you have Gn, which is single group, and G to the I, modulo G to the I plus 1 is abelian. This is the definition of a solvable group. The polycyclic group is the same, but the quotient is not just abelian, the quotient each time is cyclic. So this is the definition of polycyclic group, but to be polycyclic is the same as to be solvable and hereditarily finely generated. So and it's easy to show the equivalence. So basically, this is straightforward corollary exercise. It's more famous than the exercise that every linear solvable group is polycyclic. It's not true in general. In general, you have solvable discrete group which are not polycyclic. Like maybe probably you know the Lamplighter group is an example. It's a two-generated group. What? Sorry? No, I want a finitely generated group which has a subgroup which is not finitely generated. So
but you said that. I mean,
anyhow, for solvable group, it's not true that if you're finitely generated, then every subgroup is finitely generated.
so you do need connected in the exercise?
Excellent. Compactly generated solvable Lie group is HC.
I mean, the Lamplighter is not a complete generated. So
The Lamplighter is not a Lie group over the real. It's not. Yeah.
Oh.
The Lamplighter group in particular is not a linear group. You don't have a faithful. It is the consequence of that. You don't have a faithful representation. You can do it. I mean, I assume discreteness, but you don't really need it. The Lamplighter is not. The Lamplighter is a two-generated group which admit an infinitely generated sum. For linear solvable group, if you are finitely generated, then any subgroup is finitely generated. And more generally, if you are compactly generated, solvable linear group or solvable Lie group, then any closed subgroup is compactly generated. And it's slightly more general, but this is it's not a hard exercise. You prove it by hand, as you prove anything for solvable group by induction on solvability group. I mean, you first do it for abelian group, and then for abelian group is almost like proving that Zn has this property. Every subgroup of Zn is finitely generated, and then you move on to if G is a, let's say, a connected Lie group, then G prime is a small group, and the quotient is abelian, and you know the property for the quotient, and by induction using the property for that, and you have to say a few words, but technical words, but it's this is not a hard exercise. I mean, it's a good exercise, and it's good to be aware of this notion. So I gave you two exercises, and modulo this exercise, I'm going to give you an elementary proof for most of theorem, and let's do it here. So most of theorem say that connected solvable Lie group has property M, or completely generated solvable Lie group has property M. I will use a bit structured theory of Lie group. Basically, I will use Lie theorem. The proof of most of theorem. Let G be a compact. I could say connected, generated, solvable Lie group. I could say connected, but the only reason I say compactly generated is because I want to emphasize this property, because soon we will forget Lie groups and talk about totally disconnected groups, and then the situation is much more mysterious, and the compact generation is an important notion there. So compactly generated solvable Lie group, basically it says that modulo the connected component is finally generated. Let H be a closed subgroup. H be closed co-finite, meaning the G mod H carry probability measure, subgroup, and we want to show that H is uniform. So, okay. First, up to replacing G by a finite index subgroup, so this is something we didn't have to do if we were if we started with connected group. We may assume that G prime is nilpotent. So this is Lie theorem. Lie theorem says that a connected solvable Lie group, connected maybe I should say, I should explain that. First, you have there is the Edo-Iwasawa theorem. Edo-Iwasawa theorem tells you that every Lie algebra admits a faithful linear representation. On the level of Lie groups, it means that every, let's say, connected Lie group admits an almost faithful, admits a linear representation whose kernel is central, is discrete and central. And here we don't care about discrete central stuff. So we may assume, we may reduce to the case that that G is linear group. Now for let me just finish. For linear Lie groups, you can look at the Zariski closure and take the Zariski closure over complex, and then the Zariski connected component is a finite index, and it's connected, complex, solvable Lie group, and that group by Lie theorem is conjugated to the into the upper triangular solvable group. And for the upper triangular solvable group, if you take the commutator, you get the upper triangular unipotent group. So this is why G prime is nilpotent. So basically, by this statement requires some Lie theory. Basically, it requires two things: Edo-Iwasawa theorem to move to assume that G is linear, and then Lie theorem to by another finite index to. Okay, so I'm just saying it in two lines here. One line, if about, but yeah, it relies on two theorems. So you have a question?
Like once we assume the group is a linear group, so we don't need to say like connected, not connected. Like we have this also over non totally disconnected groups, right? Oh, everything is still if they don't have to have a lattice, if they have to.
Well, it's true that there is an analog of Mossel theorem for let's say Lie group or linear group of a local field, but it's not the same. It's again it's also, you can find it in this paper, but we do it also for other local field, but it's a different, slightly different group. And so let me discuss the classical case here. So we may reduce to the case that G prime is nilpotent. If you want, you can start with that. Just say discuss solvable linear group connected, and then you just hear. So how do we proceed? So let Z be the center of G prime. G prime is important, so we take center. And let F be, let's say, Z times H, the closure of Z times H. Now I say F contains H, so F is cofinite in G. And now we can argue by induction I should say on what? So induction on the importance rank of G prime or F prime, whatever. By induction, let's say on the rank or on dimension on, let's say, on the rank, the potency rank of G prime, we see that G mod F, which is isomorphic to G mod Z mod F mod Z, that is known. So, F mod Z has smaller importance rank. Sorry, G mod Z has smaller importance rank than the commutator of G has rank R, so the commutator of G mod Z has rank R minus 1. So by induction of the importance rank commutator, we deduce that F is cofinite because F has cofinite volume because it contains H. The group that contains the subgroup of cofinite volume is also a cofinite volume. So this allows us.
Why is Z normal in G?
Z is even characteristic. Z is
in G prime. It's characteristic. But in G.
No, but if it's
it's characteristic in characteristic.
Yeah, in characteristic in normal or in characteristic.
Yeah,
yes. Yes. So Z is the center of the cone. So it's characteristic in G. So therefore it's normal. So so we have that. So this allows us to assume things we may assume. That H times Z is dense in G. And assume that F is equal to G. Okay. Next, consider N be G prime intersection with H. And I claim then N is normal in G. Okay. Why is that? Do you see why it's normal in G? When G prime is normal in G, and I claim that the intersection of G prime with H is also normal in G, and the reason is that because we're in this situation that yeah, so okay, certainly. So why is that? Okay, then H normal in G since it is normalized by Z and by H. Okay, you see Z is the center of G prime, so Z normalize any subgroup of G prime. Z commute with anything in G prime, so it's normalize any subgroup of G prime. So Z normalize N, but H normalize N because G prime is not correct. Okay, but H and Z is less. So if this normalize N and this normalize N, they're not succeed. So N is normal. Okay. So we need to show. So we are left to show that H mod N is compact, is uniform. So basically we can divide N. N is both in H, N in G. It is normal there, normal there. We can divide. We need to show that G mod H is compact, so it's enough to show that G mod N would be compact. Okay. And what do we know? That H mod N, however, H mod N is a compactly generated okay, because of the exercise that was here before, G is compactly generated, so any closed sub, so H is compactly generated. Compactly generated a billion. So by the exercise implies that
You mean G mod N?
okay. Let's call this let's call it by a name. Call it A. A is compactly generated a billion cofinite sub of G mod N. Hence, by the it's you see, it's really bring this theorem to elementary, yeah. Any question? Not to do the exercise that I gave you, but the exercise is not I mean, I don't have a very nice proof, but even the proof that I have. So yeah, that's most of the theorem. And it's true that there are plenty of generalization of Mossel theorem. So in particular, there is the analog of Mossel theorem for every linear group over a local field. So it would p-additive group, group over positive characteristics, and so on. But it is not true in general. So that every locally compact solvable group encompasses the end. So this will be what I want to discuss now. But before that, let me give some dynamical interpretation for this question, theorems. Question? So some, let's call it dynamical interpretation. So I want to define two notions for a probability measure preserving action. Let G be, let's say, a local compact group acting, okay, and X M probability measure preserving G space. G acts preserving the measure, like the action of G on G gamma and so on. And then there are two definitions. Definition one, the action is spectral gap. Gap if there is, let's say, K G compact and epsilon positive, such that for every F in L2 of X, so it's a square integrable measurable function, such that the integral of F equals 0. So basically, this is sometimes called L20 of X. That's how we note it's a co-dimension 1 subgroup of L2 on the function of the integral 0. The orthogonal to the constant function is 1. The constant function are the invariant under the action. And the spectral gap that I'm now writing the definition is a stronger form of ergodicity. Say that there are no invariant function except the constant. So L20 has no invariant function. And now I say that this can be measured such that for every such F, there is a G in the compact set, and such that if you want the difference between let's call it L2, LG of F minus F is at least epsilon. So you remember what is LG? It's the left regular action. So LG of a function at the point X is by definition f of G into X. That's how you act on function. So which means that the function move. Okay, this says the spectral gap. This is called spectral gap. It's related to eigenvalue of the Laplacian. Okay. This says this is the definition of spectral gap. It's related to property T that we discussed in the last course.
The inequality is this way or the other?
Sorry?
The inequality is
This way. So basically, if you want a group G as property T, if any ergodic PMP action of it has spectral gap. I mean, that's actually property T formally is stronger. It says that any unitary representation has spectral gap, but it's actually equivalent. So this is one definition for PMP action. And the second definition that I want to discuss is the stronger bodicity. The action is strongly ergodic.
It's like fixed epsilon for all the.
There is,
No.
yeah, if there is I fix a compact set and fix it. So many times G is just a cyclic group. And then the compact set that you're discussing is just the transformation that generates the cyclic. And yeah. And there is some epsilon such that this. We discussed locally compact group, so it is done. And the other definition is of stronger ergodicity. And action is strongly ergodic. This is also, of course, a form of strong ergodicity. It's strongly ergodic. If you have a sequence of asymptotically invariant sets, then it must be because of the obvious ring. So if there is K G compact such that the following one, such that if AN are subset of X are let's say K 1 over N K asymptotically invariant, let's say K asymptotically invariant sets. So that means that let's say that AN is K epsilon N invariant with epsilon N goes to 0. Then the measure of AN goes to 0 or 1, and the measure of the complement goes to 0. So it means that it's because of trivial reason. So you cannot have sets of measure 1/2 which become asymptotically invariant. That's what I'm saying. And should I explain what is K epsilon N invariant, or I think you know, right? The symmetric difference of the measure.
What is the word there? Such that if A in X are K.
If you have a sequence of asymptotically invariant sets,
Asymptotically invariant, okay.
then it's because that. And basically, it's the same as definition 1, but here I restrict myself to characteristic function, and here I allow all functions.
Okay.
So that's basically what it says. That's stronger ergodicity, and
So 1 implies 2?
yeah, that's what? Sorry.
Hold on, epsilon asymptotically invariant means the symmetric difference of A and GA is less than epsilon for some G, for every G.
Is for every G.
For every G.
For every G. Yeah, that's mean K epsilon. And for every G in K, the symmetric distance. And
if you asymptotically invariant for all epsilon.
Yes, so if you want, this is an exercise just to understand better the notion, is that spectral gap implies multiplicity, so exercise. Graph implies multiplicity. And obviously, if you want to know what it means, a group has property T. If yeah, then every ergodic action is vector graph, and therefore every ergodic action is solely ergodic. But the converse is also true. A group such that every action is solely ergodic has probability. That's Gelander value. And one Gelander. And but these two notions are equivalent for five groups. Even for finely generated amenable group, you can show that these two notions are equivalent. So an action is vector gap, even only if it's only a group. But for general, these notions are not the same, and these notions are not the same. So let me just quote, or let me just, I don't want to discuss too much this notion, I just want to say two results from you can again find in this paper that I'm discussing today. Two results, proposition one. Proposition any transitive PMP action of a locally compact group is strongly. One proposition. So the action of G on G mod gamma, if gamma is the lattice, is always strongly ergodic. This is proposition. I will not put, but it's not very hard. The other thing I want to say is the notion of a weakly compact. So this is the definition of Margulis. Sub H in G is weakly compact. Let's say a cofinite sub H in G is weakly compact. If the action of G on G mod H is spectral gap. That's the definition of Margulis, and I don't think it's a good name, but Margulis proved the following statement. So here is the proposition of Margulis. That co-compactness implies weak. If you have a co-compact lattice in every locally compact group, if you have a co-compact lattice, then it's weak. That's a proposition. Yeah, you can do it yourself. Maybe it's a star exercise. It's not very easy, but it's elementary. And this is the motivation for the name. And here is another proposition from the paper that I'm discussing is the following. For a amenable group, By the way, so Margulis proved that, and Margulis also proved the following theorem. This notion of spectral gap is very, you use it in many proofs. So, so Margulis proved the following theorem is that lattices in semi-simple group are always weakly compact. It's somehow not related to the topic because today I'm discussing amenable groups, but it's related to the main topic of this course, which the main motivation for me to study lattices is because lattices are mostly in lattices semi-simple group, and there, okay, you know that if G has property T, then every lattice is weakly co-compact because the property T trivially implies weakly co-compact. But Margulis showed that every lattice in every semi-simple group. Now, okay, you can find a new proof of this theorem in my recent paper with Ari and Margulis.
I don't understand. You say the proposition is that co-compactness is equivalent to weakly co-compact, and then you're saying
no, co-compactness implies weakly co-compact.
It looks okay. The
No,
S
to be weakly co-compact is weaker than co-compact. So in particular, every lattice in a group with property T, it's weakly co-compact.
Okay.
So SL3Z is weakly co-compact in SL3L, but it's not co-compact. But yeah. And now let me, before the break, state another proposition from this paper. That for a amenable group, it's actually equivalent. If G is a locally compact amenable and H in G a cofinite subgroup, then H is co-compact if and only if H is weakly. So basically, what it says that for a amenable group, if you find a subgroup which is cofinite but not co-compact, then you found a transitive action which is strongly ergodic, but don't have spectral gap. Which somehow, for instance, is a counterexample to the generalization of something that I said before, that for finitely generated amenable group, for discrete amenable group, it's a classical theorem. For discrete amenable group, spectral gap is equivalent to small group. And for locally compact amenable group, if you find a lattice which is not co-compact, so a counterexample to the generalization of Mosso theorem, if you find such a group, then you found an action G on V1 gamma, which is strongly ergodic by this proposition, but does not have proper spectral gap by this proposition.
Why does this mean no spectral gap?
The weak compactness is by definition that the action is spectral.
So if you find a non-compact.
Yeah, and we will find. So that's what we will do after the break. After the break, we will prove the following theorem. There is a locally compact actually metabillion, which is two-step solvable. It's much more than amenable. Locally compact metabillion. G with a non-uniform. Actually, we will see that it has plenty of non-uniform lattices. In fact, uncountably many non-uniform lattices and only countably many uniform ones. So this group has plenty of actions which are, it's amenable, it's even metabillion, it has plenty of actions which are not, do not have spectral gap, but are strong unibody. So this is, I gave you the dynamical interpretation of so this is a counterexample generalization that you would expect, or at least Yves Benoit and Jean-François Kant thought it's true. They conjecture, they actually thought they proved it, that every lattice in a local in a middle group is co-compact, but no, we'll see another example. But then, okay, so I will explain the counterexample, but then there's still related interesting question. Maybe the generalization is true under some additional literal assumption, which is compact generation that I try to emphasize at the beginning. Okay, let's have like 15 minutes break.
więcej mają
So Tal had remarked that in my assumption that G is compactly generated, there is some, you need some, either the G is linear or connected, because the example that I gave, the lamplighter, no, that's not, it's not a country. No, actually, forget that remark. No, it's not.
Can you explain?
No, because for discrete group, it's still true. Discrete group obviously has probability.
No, but what is the exercise of the
for the exercise. Okay. Yeah, for the exercise, if you want, it show that linear Lie groups. Yeah, the exercise is for linear.
And how do you know that G forms of
This is from Lie theorem. Lie theorem says that if you're connected.
Yeah, but you don't know it's linear.
No.
By either your Sava theorem, and then you apply Lie theorem. And, okay, so now I'm proving the theorem that there are even Machiavellian groups with meeting a non-uniform lattice, which is a counterexample to the question that we discussed. And basically, that's the topic for now. I'll give you the proof, the construction. So let Pn or let Qn be prime power such that the sum finite. You want this equivalent to the fact the product of Qn divided by Qn minus 1 just that they grow fast enough. You can take them prime, you can take them prime power. This will work, both will work. And let FQ the corresponding field, conic field, with the field of Qn element. And F Qn star. So by this I denote also the billion derivative group, and this is the multiplicative group. And what to say about this field, about this let say Kn is a group, Fqn semi-direct or which is the same as if you want the upper triangular A1 B such that the AX is big corresponding to this bit. And using F down. So here is an exercise for you. I'm also telling you why it's true. That denote by sigma all the elements of the form A minus 1 A FQ. Now, it's a sum.
Why do we have an N?
Sorry? Yeah, let's, I mean, for this discussion, yeah, let's okay. And yeah, for this discussion, later I take Q to be Qn, A to be N, but for now I just discussed. And so this is a subgroup with the, you see why it's a subgroup? So
We said that is a lattice, right?
now I discuss finite groups. Lattice in finite groups
No,
is
but
not a
in
very
the
interesting
multiplication,
group. Sorry?
the multiplication of all the.
No. For the moment, I discuss this finite group, and the way to see that it's a subgroup. So here is the how you solve it. You look at that group, A1 0 0. This is certainly a group, and then you conjugate. I don't remember exactly. But see, maybe this. That's a conjugation. That's the inverse of that. And do you conjugate by that? No. You should certainly not do that. Okay, wait a minute. Is that true? I think so. If that doesn't work, then move this to -1.
Yeah, I think that.
Like this. So you see, this is how do you see that it's a group. Okay, now I will introduce a group. So now I will tell you what is the. Let's G be this semi-direct product. I look at this FQN. It's a compact group actually. It's an infinite product of finite groups. So that's a compact group acting on the direct sum of FQN. For this, so if you want, this is compact. This if you want, I need to tell you what is the topology, but basically it's a compact extension of discrete group. If you want, this is a group, and topology is determined by saying that by the following requirement that this group, let's call it K, that K is open compact. K is the typical product, and by saying that it's open compact, so basically, how do you introduce topology on a totally disconnected on a group such as how do you introduce a totally disconnected topology on a group? You declare one subgroup to be open compact, and if you don't always allow to do that, but what allows you to do that is if this group is commensurated by the so to be a totally disconnected group is actually an algebraic. It's logically data, but it's also algebraic. So the topology is determined by declaring that one group is open compact, and you can do that as long as the full group commensurate the conjugation of any and this is the case here.
This is just the product topology, right?
Sorry? Here we take the product topology.
Yes, also just take the product topology of this topology. And you never, when you have the same direct product, you just take
This is the product topology. Yeah. But another way to say it is that the topology is determined by declaring that K is open compact. So K is open compact, but it's not normal. The normal subgroup is this discrete, and you will see that I will show you that in that group you have non-uniform lattices, but you will see that this notion, which has also dynamical interpretation, is very sensitive. If you do not preserve, if you move to finite index subgroup, to co-compact, you take this co-compact subgroup is already abelian, discrete and abelian. You have a co-compact subgroup, which is discrete abelian. In abelian group, abelian group certainly have property M. Every cofine subgroup are measure of quotient. So we see this reflect that this phenomena is sensitive.
Tsachik, it should be FQ and star acting on him.
FQ, yeah.
And an element in K should be with finitely non-unit elements?
So not just in K, in G. So what is an element in G? So this is here you can have all the entries, whatever you want, but here only finitely many are. It's a direct sum. That's the difference between direct sum and direct product. So let me just say, inside G, I will. So a typical element in G, and element in G can be written as a sequence AN BN such that AN F UN star BN F N and BN equals 0 or almost all N. Starting somewhere, BN
So AN and BN are contained in the product and the.
so G is just
Not in a single FQ and star, right? In the product of. Yeah, well,
So if you want, we can write Gn to be the group of all such sequences, such that B, this would be M, such that Bn equals 0 for all N, which are P. Then you see the GM is compact, open, and G is the direct limit of the union P. So in a sense, G has more than one reason to be amenable. One reason is that it's solvable, it's Machiavellian, and right reason to be amenable. And here is the topological reason to be amenable. It's a union of compact opens, the direct union of open compact. Direct limit of open compact subgroup. So it's both, for both reasons, it's amenable. So this is G. And now I tell you what is the lattice. Find gamma to be of the sequence A N minus 1 such that AN star and AN is 21 almost sure. So I can find many. So this is gamma. And by the exercise that we had before, gamma is the group. And now I claim that two stuff. I claim that gamma is discrete. And I claim three things. Gamma is discrete. The volume of G mod gamma is finite. It's a lattice, and it's not unique. And the exercise for you, okay. Just prove that, then.
Tsachik, can you maybe say what is metabelian?
Metabelian is just that the commutator is abelian. It's two steps of. The fact is that abelian group are, as simplest group you can imagine, but a meta-billion group are
Meta-trivial.
they are quite interesting, but still quite easy to deal with. So I mean, as you see, not completely easy. There are interesting phenomena in meta-billion group, but it's much easier to deal with meta-billion groups. It's a general phenomenon in algebra that you can prove many results from meta-billion group, which become infinitely harder if you try to do it for three-step solvable. Three-step solvable, it's a wild world. It's really much more complicated. Two-step solvable. But this example is still given for meta-billion group, and even here you have interesting stuff. So the theorem that is that gamma is a non-uniform lattice. So it's discrete, cofinite, but not compact. And how do you prove it? You just okay. First, why it is discrete? So you tell me. What? How do you show that the subgroup is discrete? You find an open set that intersects it trivially. What is the open set?
G0.
K. G0 is K. So proof gamma is section with K is trivial, and therefore gamma is trivial. Okay. So how do you show that it's okay? First, I tell you how do I normalize the Haar measure. So I will normalize the Haar measure. Normalize the Haar measure. Such that the measure of K is 1. By the way, so this K belongs to Gn. So K is a subgroup of Gn. So what if I normalize the Haar measure of it to be 1, then it's already introduced what is the Haar measure of Gn. So okay, it's the restriction of the Haar measure of G. If you have a group and an open subgroup, Gn is open in G, so the Haar measure in G induce the Haar measure in Gn, and
K is just all the b's are 0, like the
yeah, K, if you want, it's yeah, K is what? It's isomorphic to the product of F, Q, and star, and it's equal to the set of all A n 0. And it's G0. So or G0 or G -1. Yeah, G0. And okay, now let's say what is gamma n? Gamma n will be the intersection of gamma with Gn, which actually is a finite group. Why? Because gamma is discrete and Gn is compact, so that's a finite group. And okay, and now you see two things. So first, what is the index of Gn? Gn -1. What is that index? So can you tell me? Yeah, Q. And what is the index of gamma n? What is in the index of gamma n minus 1 inside gamma n? You remember what is gamma n? Gamma, yeah. Yeah. So what should I write here? Human. Okay, so steroid moment. So gamma n is I have 1, 0 all the way starting at n, and up to there I have whatever I want. So but this an now belongs to fq and star, so there only n q minus 1 possibilities. So we see what is the co-volume of
Gamma n minus 1 is it's not normal in gamma n. Right?
sorry?
Gn minus 1 is normal in Gn, but gamma n minus 1 is not.
No, Gn is not normal. No, nothing is normal. No, this is not normal.
Okay.
Yeah.
It's not.
This is
Can.
This is fine. I mean, this is open. These are compact, open. These are both finite groups, but nothing is normal nowhere, except that the direct sum is normal in G. But now let's see what is the volume. Let me write it like that. What is the measure? What is the volume? It's using of Gn modulo gamma n. Okay, I don't know what it is, but it's the volume of the previous step, Gn minus 1 modulo gamma n minus 1 time Qn divided by Qn minus 1. This is because of the line law. So this tells me two things. Okay, first, if I continue on the way, and I know that for G0 is K. So and gamma 0 is the trivial group. So and the High measure of K is 1. So by this I will deduce the following. Deduce two things. I deduce the volume of G n mod gamma n is the product of Qn divided by Qn minus 1 and one n, right? This is one thing. Realize? Which is finite by the assumption. Okay, not finite. So this implies now, okay, but this requires an explanation that the volume of G mod gamma is the product from 1 to infinity of Q m divided by minus 1. And so I need to explain why this is true. But this will, and I claim that this implies, okay, I didn't this I need to justify this. But once I justify this, it will tell me two things. First, it implies hence gamma is a lattice and non-uniform. So it is a lattice because this is finite, so the covolume is finite, and it's non-uniform because this product is infinite. So let me say something more general. So I explain now this implication. So you have a question not related to the implication?
Yes, just one.
Yeah.
You said that the sum of all 1 over Kn is also finite, right?
1 over Qn.
Qn, yeah. So maybe you can use the volume theorem for this,
For what?
because the volume of G mod gamma is
For what? You ask about the equivalence between this and the fact that this is a elementary. I mean,
one just.
take logarithm and you.
Well, this is
No,
just
no,
one
let's
over one
go on.
over
Just
one over one's one over.
just another way to see that the volume of G mod gamma is finite.
Okay, I don't see what you say, but let me go on with my plan and later if anything is not clear or you have a simple way to say.
So why did non-uniform?
Yeah, I will explain two things. So first, so there are two claims. Claim one, if G is locally compact, and Gn in G open, gamma lattice G, then
Did you explain why this is the volume? Just this is one.
I explain now. So the co-volume, or let's say gamma is discrete group. Gamma G is discrete. Then the volume, let's say open and let's say also the union of Gn equals G. Then it's the volume of G mod gamma is the limit of the volume of G and mod gamma intersection. This is one thing. And moreover, gamma is co-compact. If and only if there is equality, the volume of G mod gamma equals to the volume of Gn gamma n for large n. So this stabilizes. And you see, if I prove this claim, this claim implies this implication. Because it would tell us that this is the volume, and it would tell us that this is not stabilized. So this is an increasing function. And the reason for that is by looking at the fundamental domain. Take a fundamental domain for gamma n inside Gn. It's contained in the fundamental domain of gamma in G, so you can include it. So if you take if you do it for every n, then you will get a fundamental domain for gamma and G. If you do, you say if the proof let you want omega n be consistent choice of fundamental domain for gamma section Gn in Gn. So the union of omega n is a fundamental domain for gamma in G. Therefore, if and this implies the volume. To see the last remark. Okay, so there is a question why you can choose such a fundamental domain to be consistent, and in general there is something to prove. In our case, all these groups are this. You have copper group and finite group inside, and then you enlarge it. So it's very easy to do that. But you can do it in general. You can always increase the fundamental domain. Yeah, and the other, and to see the moreover stuff, you say, okay, if G mod gamma was compact, then I had a compact fundamental domain for G. One of these Gn would contain this compact fundamental domain, but this is the open cover of G. And then you see it's already the fundamental domain is containing a smaller subgroup, then it's already the core volume of this. So this is why it's there. So that's a proof of the claim, and therefore the proof.
Can you repeat the last
The explanation of this moreover?
Yeah.
Okay. So moreover, if gamma is uniform, if gamma is uniform, there is a compact relative compact fundamental domain omega in G from gamma. Gn is an open cover, which implies that Gn contains omega for large n. It implies, in particular, that the volume of Gn of gamma intersection Gn is the same as volume of omega in gamma, so this sequence step. Okay, so this proves the theorem.
So we can replace instead of primes, we take prime powers and
Yeah, I did. I thought about, that's why I wrote Qn. I thought about prime power.
Then you change the q and minus 1 to the size of the multiplicative group or something like that.
The multiplicative group is,
If it's a prime power, is it?
yes.
No.
Sure.
Ah.
Yeah. Yeah, it's, yeah. The multiplicative group is the only non-invertible element in a field is there. We can think about, you can try to make general construction for other ring if you want, but anyhow. So here's the exercise for you.
Does this group have a uniform lattice? Oh, no.
Yeah.
Okay, that's the whole right side.
Yeah, right. It has a uniform lattice. So yeah, the discrete group, the direct sum. But basically that's all. There is only one commensurability class of uniform lattices. So if you want, so here's an exercise, the same G. the same G has many non-uniform lattices but only amply many uniform. So you see, so that's yeah, that's the example. But, and here is the remark, G is not completely generated. G is not complete. So G is not other thing as well. Maybe you can define the question. This is somehow the most interesting, in my opinion, open problem related to this stuff. So it would be great if you can solve it. I think it should be solvable, but it's not obvious. So let me just tell you some remark. Theorem. A compactly generated abelian group has property M. So again, I will not try to prove, but it's, again, it's here in this paper by Uri, Pierre Emmanuel, Shachar, and me. Discuss lattices in a linear group and mainly this property M, and we give many conditions that imply property M, and in particular, one of them is compactly generated with abelian group. And you can generalize it to a bit more, but it's already an open question. What about? But that's not an exercise. I mean, it's an exercise, but would be a nice PhD. Or what about three-step? So. And general solver, and general. So yeah, so this would be great. What we don't know. Compactly generated, three-step solvable, does it have property M? Yeah, that's we can do it. In our paper, there are a lot of information, but we don't know to do that. And yeah, there are other literature related. Okay. Do you have questions about this? So, yeah. I'll tell you about how we will proceed. So next week I will give an overview about lattices in same simple groups, rigidity theory, arithmeticity. We'll explain, for instance, why superrigidity implies arithmeticity. I will describe Borel-Rishander theorem. I will show other application of rigidity. We'll discuss motor rigidity, local rigidity, superrigidity, arithmeticity, and application. That will be kind of overview because, yeah, it's a really beautiful theory. but the theorems, the rigidity theorems are usually hard, so I will not give a proof for any of them. I will show that superrigidity implies repeaticity, but I will not prove superrigidity. That's if we decide to do that, that would take maybe a couple of weeks or a few weeks to do that. But I choose to take a different trail. And by the way, Uri is like the world expert in the rigidity stuff, generalizing Margulis theorems. Uri and Alex Forman, they have a beautiful generalization of that. But this is material for another course because I'm taking a different trail, but I will prove Borel-Arishandon theorem. That's arithmetic groups of lattices, and I will explain Margulis proof of that, which is it's quite clever proof, which is not the classical proof. It's not the original proof. It's already. It is also important and beautiful. It's what's called reduction theory, which you can find in many textbooks. Unlike Margulis' book, which is hard to find, even you cannot find his paper online. So yeah, but but it's a beautiful and useful proof. And so that's the next topic. After the overview of lattices and rigidity, I will give that. And then we discuss a bit more about lattices, basic properties, and move to advanced algorithms. Yeah, so that's. So if you have a question about the course today, you